Here's sort of a cool way to take any metric and turn it into a metric for which no 2 points are distance 1 or greater apart. Exercise 5.10, let xd be a metric space, and for any points x and y in the set x, define a new metric, capital D, by capital D of xy is going to be the little d of xy divided by 1 plus little d of xy. So we're taking the original metric little d and defining a new metric capital D in terms of it. We want to show that capital D is also a metric on x. So first property of metric, we know that little d is a metric, and so it's always greater than or equal to 0. And that means that in the definition of capital D, the numerator is greater than or equal to 0. Denominator is certainly greater than 0, and so the quotient is well defined and is greater than or equal to 0. And okay, well, when is capital D equal to 0? Well, that's exactly when its numerator is equal to 0. And since little d is a metric, that happens exactly when the points x and y are the same. So capital D of xy is 0 if and only if x equals y, as required. All right, and the second property, we want capital D to be symmetric. By definition, it equals this, and then since little d is symmetric, we can change the order of the y and the x in both places, and it becomes just capital D of yx. So the capital D being symmetric follows quickly from little d being symmetric. And as easy as those two are, you'd think that maybe the third one would be too, but it's not. We want to show that basically using the fact that the triangle inequality holds for little d, we want to prove that the triangle inequality holds for capital D as well. Okay. Now I remember being assigned this problem in college and never being able to figure out the answer, so it's a little bit challenging, and I still don't have a great way of explaining how to come up with the answer, but I'll tell you what it is. To simplify things, let's define a to be the distance from x to y, b the distance from y to z, and c the distance from x to z with respect to this original metric little d. And so since that's a metric, we know that for any x, y, z, we get a plus b greater than or equal to c. Okay. And we want to prove that this inequality holds, because this first fraction here would be capital D of x, y. This would be capital D of y, z, and this would be capital D of x, z. Okay. So somehow this inequality should imply this one. And let's see. Well, the first inequality, if you divide both sides by c, and I guess you can do that because, well, c is greater than or equal to 0, and if it's 0, then this is 0 and we're done, right? This inequality has to be true. And so suppose c is non-zero, and then we can divide both sides by it, and we get this. Okay, so we can assume that this is true. And the second inequality here is equivalent to, well, let's see, this time I want to multiply both sides by 1 plus c over c. And, well, again, kind of don't have to think about the c equals 0 case. So suppose c is non-zero, then I can do this. And if I sort of rearrange things a bit, I get that the inequality I'm aiming for is equivalent to this one. And then if you distribute fractions, you get this. All right, so if I can prove that either of these hold, then I'm done. Now I need to break this up into a couple cases. First of all, suppose that a is greater than or equal to c. Right? We know that a plus b is greater than or equal to c, but maybe we don't even need b. Maybe a already does it by itself. Well, then in that case, just add a plus c to both sides of this inequality. And then, all right, everything here is greater than or equal to 0, and I'm assuming that c is non-zero, so I can divide both sides by the right side, and I get this. And so that tells me that the first summand here is already greater than or equal to 1. So certainly when I add something else, which is non-negative to it, the sum is going to be greater than or equal to 1. So I'm done in that case, right? And a similar argument holds if b is greater than or equal to c by itself. Then I'm going to get that the second summand here is greater than or equal to 1 by itself. And so this inequality will hold again. Good. So that takes care of the case when a and b are, when one of them by itself is greater than or equal to c, or maybe both of them. How about if neither of them is? So in other words, a and b are both less than or equal to c. Okay, well, this time I'm aiming for this version of the inequality. And all right, since a is less than or equal to c, that means my denominator here is smaller than my numerator, so the fraction is greater than or equal to 1. And similarly for the same fraction with b in the denominator instead of an a. And so each of these fractions are greater than or equal to 1. And this expression on the left up here, okay, this fraction is greater than or equal to 1, so this product here is greater than or equal to a over c. Similarly, this product is greater than or equal to b over c. But we decided that we knew that the sum of those two things was greater than or equal to 1. Okay? So put it together and we have this inequality, which was equivalent to this one that we wanted. And we're done. Capital D satisfies the triangle inequality and is a metric. All right, now part B, explain why no 2 points in X are distance 1 or more apart in the metric D. Well, just look at how it's defined. Certainly, well, the numerator is greater than or equal to 0 because little d is a metric, and the denominator is bigger than the numerator, right? And so when we divide them, we get something less than 1. So capital D is always less than 1.